Luke, welcome to Monero Magazine, man.
Thanks. It's a pleasure to be here.
So, as you know, we're just chatting off air. I want to speak about membership proofs today. As I'm sure you're aware, all cryptographers, developers are aware that you guys are absolutely a special breed. So, I've got like a definition from Google here. A membership proof is a basic interactive proof for a statement of the form X divided by INL, where L is some formal language, is often called a proof of membership. Now, obviously, that makes total sense to everybody reading, including myself. But just in case it doesn't, just for the absolute idiots out there, right? What is a membership proof, firstly?
Uh, First of all, I'd have to check what notation you're using for your statement. But a membership proof is generally just saying, out of this list of items, this other element exists in it. So if we have, the numbers 1 through 10, yeah, the number 5 is somewhere in there, and here's a proof of it.
So, how does that relate to Monero then? How is this useful to Monero?
So Monero is planning to evolve its privacy protocol into Seraphis, and with Seraphis, one of the components is a membership proof. So what we do is under prior discussed plans for Seraphis, we pick 128 outputs on the chain, and then we do a zero knowledge membership proof. So out of those 128 outputs already on the chain that we know exist, we know what 128 outputs they are. We say this new output being used in the transaction is actually one of those outputs, just slightly hidden, in order for no one to be able to tell them in any way are linked together. But despite having a slightly different bit of randomness, the everything else is the same. The owner of it is the same, the amount is the same, everything else.
So, what problem specifically is it solving then?
It's solving the privacy on the sender side. When you send Monero, obviously you don't want to say what transaction you're or what output you're spending, because that would enable revealing the transaction graph, tracing funds, seeing who else you interacted with. So membership proofs are how we achieve sender privacy. And under current Monero, we don't technically use membership proofs. Right now, what we use are ring signatures. Ring signatures are membership proofs combined with a signature. So we'll have 16 outputs, and we'll say these 16 outputs exist on chain. Here's the 16 we're talking about. And I own one of those outputs, and I'm spending it here. So it's a slightly different statement, yet by breaking the statement into two parts, one is I am one of these old outputs, another is I am the owner of this output and I'm spending it in this transaction, we get to use a lot more efficient proofs to prove membership, which is why even before my work, Seraphis was discussing moving from just 16 outputs to 128 outputs.
So, how does it work then? Break it down for the average idiot like myself.
So I think that's going to be a bit too much to get into. Basically, there's a lot of math behind it there's a lot of math.
Okay, is there even like a simple way to describe the main concepts?
I really think just staying at the problem statement level is best, saying, there's 128 outputs and this output is one of those, but you can't tell which of those it is. It's just a cryptographic proof for that statement, and I don't think going any further would help today.
Okay, so just to clarify, so with membership proofs, are you still technically posting the key or the address on chain, so to say, as you would be technically with ring signatures?
So with ring signatures, you specify which 16 outputs you want in the ring. And with the prior discussed membership proof for Seraphis, which the Monero developer community refers to as Groodle proofs, Groodle. It's a combination of the names Groth and Boodle, because they were the ones who put forward the membership proofs we're looking at using, or were looking at using, kind of still are. We'll get to it. Um, with that, yes, you would still specify which 128 outputs you want to say your transaction's input maps to. But of course, just like with ring signatures, just like with ring signatures, Seraphis membership proofs don't reveal which output you're actually talking about, just that it's one of 16 or one out of 128.
Okay, so when you're talking about 1 out of 128, you're talking about posting your spending key or your public
No,
address or
just like you select so when you create a Monero transaction today, it uses a ring signature. So the ring signature works by you have an output and you select 15 random outputs from the Monero blockchain, and that forms a ring of 16 outputs. With Seraphis, a similar process happens if we move forward with Grudel proofs. With Grudel proofs, you have your output, you want to spend it, and you select 127 random outputs on chain, and all anyone can tell is that the output you spent is 1 out of 128. Just like how with the current ring signatures, all people can tell is that the output you're spending is 1 out of 16. And this is purely on the sender privacy side. For amounts, obviously, we use confidential transactions. Currently, we use Bulletproofs Plus to hide amounts. And then for receiver privacy, we currently use and still will use stealth addresses.
Okay, so clarify for me here. So we have ring signatures is a ring of 16, right? And is it Grudel proofs?
With Seraphis, that was initially planned and to use Grudel proofs, and Grudel proofs increase us from 16 to 128.
So then membership proofs. Totally different from Grudel proofs, I'm imagining.
No, Grudel proofs are membership proofs. What my work was on full chain membership proofs, which means instead of selecting 16, instead of selecting 128, it's selecting literally every output that has already existed on chain.
Okay, gotcha. So it literally becomes a ring of every output in the history of mankind, of Monero's mankind, anyway.
That would be the simple way to put it, yes.
Okay, so what's the implications of that in terms of increasing the data on chain and all that kind of stuff?
So, I can get into a few technical details, but mainly it's about reducing the ability for targeted surveillance. Right now, with ring signatures, there are some spending patterns that can reduce your privacy, like the EAE attack. It's also known as the EABE attack. It's also known as the Overseer attack, I think, in some other circles. But basically, it's when an exchange sends to Alice, and Alice sends to another exchange. If those two exchanges are colluding, they can say, well, I sent 100 Monero to Alice, and out of you received 99.9 Monero an hour later, and that 99.9 Monero came from one of these 16 transactions, and one of these 16 transactions was the first exchanges. Well, what's the chance that this first exchange transaction was randomly selected to be in this 16 when there's tens of millions of Monero outputs and the amounts line up and it happened within such a close time period, so on and so on. So the EAE attack is kind of like one method of breaking down rings. But there's a few other patterns that can definitely reduce your privacy with ring signatures. So what the goal of full chain membership proofs is to almost remove that as much as possible. Yes, exchange one can still send, 107.4 Monero to Alice, and 20 minutes later, Alice can send 107.39 Monero to another exchange. And yeah, if you get, 107.34 Monero within 20 minutes, you'll probably be like, yeah, that's probably the same exact Monero. But it's going to require a lot more info from other sources, and it's going to remove a lot of the current statistical methods possible on today's ring signatures, which apply less, but do still apply to Grudel proofs.
In that case, would that get rid of the need for a 20-minute minimum wait time?
That's actually there for a different reason. The 20-minute wait is there because of reorgs. If someone was to say reorg Monero 5 blocks, and they move the chain, even if they don't remove any of the transactions, they just mix the order up a bit, that's going to change the order of the outputs, and any transactions which use that specific order in their ring signatures are now going to be invalidated because they were expecting the outputs to be laid out 1, 2, 3, 4, and now they're laid out 1, 2, 4, 3. So basically, when a reorg happens, it doesn't just affect the transactions that were targeted, it can affect any other transactions which use them in rings or use them in membership proofs of any type. So that's actually a distinct discussion. There are some implications. For example, I believe it was Monero, the wallet. They added a feature called Pocket Change to help users better deal with the 10 block lock. And what Pocket Change does is it just creates, I believe, 10 outputs. So if you spend one output, no big deal. You're not waiting 20 minutes. You still got 9 left. The issue with Pocket Change is it creates some bad spending patterns, and it can actually reduce your privacy under a current ring signature model. Under full chain membership proofs, they wouldn't reduce your privacy. So full chain membership. So that's the reason why other wallets, such as like I know specifically Cake has commented this. Cake Wallet hasn't integrated anything like Pocket Change due to the privacy concerns of it. Yet with full chain membership proofs, we no longer have those privacy concerns with it. So full chain membership proofs don't directly allow removing the 10 block lock, but they do change some of the properties and allow the mitigation of Pocket Change.
Would you call full chain membership proofs like a new standard, like a big significant progress away from rig signatures?
Oh, definitely. I think Monero has for years acknowledged the need to move to full chain membership proofs, and I believe Monero does have to move to full chain membership proofs. Anything else is incomplete, and Monero should never try to be incomplete about its privacy, and it never has tried to be incomplete about its privacy. We have efforts to make sure all wallets look the same. We have efforts to make sure that you have network privacy, receiver privacy, amount privacy, sender privacy. We really do like our privacy. But the issue was with sender privacy, it's very, very difficult to do in a performant manner without relying on a trusted setup or some decently new cryptography. I don't want to start using the label moon math, but I do want to acknowledge that a lot of zero knowledge work in the space could use a bit more peer review.
Sure.
So that's why Monero's used ring signatures for so long, and it was planning to move to the Grudel proofs for membership. And those have also been around for a few years and are definitely stable. The main reason that we're discussing full chain membership proofs now is twofold. It's because, one, we have an implementation. I wrote one and announced it at MoneroCon. I'm very happy to have done it. It obviously still needs work, and we're not exactly sure what the timeline on it is going to be, but it does exist, and I'm happy to have it. But the other thing is it's not using, a brand new proof. I didn't, just drink a bunch of energy drinks and get to the coding. No, it's actually built on top of Bulletproofs and Bulletproofs Plus, which Monero has already done peer review on and already has integrated for mount privacy. So it's actually using those same exact proofs, just this time to implement sender privacy.
Okay, so just to sum it up again for an idiot like myself, so you're essentially moving away from currently ring signatures, which is a ring of 16, to full chain membership proofs, which is your one out of every address that's been on the chain in the history. So thinking about that from a scalability point of view, what's the increased amount of data that you need to submit to a chain?
So I'm pretty sure it's about 2 kilobytes in input, which is about 4 times larger than our current ring signatures.
Mm-hmm.
And then for our current verification times, I'm hoping to get it down to, this is going to be a bit awkwardly phrased for anyone who isn't experienced. I'm hoping to get it down to roughly 15 milliseconds if we're verifying 10 proofs at once. But the more proofs we verify, the faster it gets. So that's why I said, if we verify 10 proofs, it's 15 milliseconds. If we verify 50 proofs, it might be 13 milliseconds. And you do want to discuss larger batches, because if it's only 10 proofs, it's kind of fine for it to take a while. We're obviously not under load. That's like 5 transactions in a block. It's only when we have, 100 transactions in a block, we really start getting concerned. But I believe that 15 millisecond mark would be 3 to 5 times slower than what was planned with Grudel proofs. And due to concerns like this, and also just the amount of development work needed, there are discussions to continue with Seraphis, yet launch it with Groodle, and later migrate it to full chain membership proofs. Because one of the great things about Seraphis is the fact that it's very modular. If we want, we can use Groodle proofs at the start, but later we can implement full chain membership proofs. And there's a few discussions on the pros and cons of that.
So what's break it down again for an idiot like myself? What is a verification time? Why is it needed?
Verification time is just how long it takes to verify the proof. And it just can't be too large. If a transaction took 5 minutes to verify, yeah, we drop down to one transaction every 5 minutes.
Sure.
And obviously, that's not what we want. With 15 milliseconds, an input, and it would actually be quite faster if we have a large amount of transactions. I just kept the batch size to 10 for these example numbers, which is actually decently small. But with 15 milliseconds in input, that says, even within 1 second, we could verify 65 proofs just on a single core. So so that definitely should be able to handle all of the transaction load Monero is currently under. I believe Monero is currently honestly, it's likely more limited with regards to its transaction sizing, just because the block limit is 300 kilobytes, and obviously we have an adjustable block size. If we need more transactions to fit in the blocks, we do, but that's the other comment. Monero isn't always filling blocks and increasing its block size right now.
So what's needed for implementation? Do you need people to look over your work? And what's the sort of, I know you said there's no real time frame, but if you give like a rough time frame for things where I know it's tough, but yeah, take it away.
Definitely can't give a time frame, but next steps is one of the things I commented on at MoneroCon. Immediately, it's getting more developers familiar with the work and starting on integrating it. Monero's current cryptography is built around this elliptic curve called ED25519. And one of the discussions to have is moving from ED25519 to what's called a curve cycle. And that's one of the things that Seraphis is this really great opportunity to do so with, because Seraphis already throws out the existing addresses. And obviously, we don't want to do that. We don't want to, throw out addresses. To be clear, funds are the same. It's still Monero. You can still spend all your old outputs. It's just you'll no longer be able to receive to your already existing Monero addresses. So again, obviously, that's not something like we're happy to do. It's not something we want to do. But Seraphis does do it for a variety of reasons. And if we move to a curve cycle, then that would also require moving addresses, because if we're on different elliptic curves, kind of different underlying cryptographic stuff, we're also going to have different addresses. So doing the two together makes a lot of sense, especially because we can very efficiently move between the two of them. It's just the whole needing to redo the addresses part that's a pain point. So there's already been discussions in the Monero Research Lab meetings about rewriting Monero to be a bit more agnostic about what the underlying cryptography is. So it could be used with ED25519, or it could be used with a curve cycle. And that would let us start evaluating the performance of curve cycles, candidates to use as the actual curve cycle, and also start letting us integrate my work directly into the Monero code base. A few developers have expressed interest in working on that. I believe Justin Berman will actually be submitting a CCS soon to do some work on that, and I will also be submitting a CCS at some point to continue developing it. And then there is some research tasks needed. Not only do we need this protocol called a vector commitment scheme proven. It doesn't have security proofs currently. Obviously, it does need security proofs. Can't move forward without them, so that will be a step. And then obviously we need to get the code reviewed, need to get the code audited, need to make sure that's all good.
So,
and it's
keep going. Sorry. No, you keep going.
I was just going to say, it's because there's all this work, there are discussions about doing Groodle proofs first and then moving to full chain membership proofs.
Okay. So it was called a curve cycle, right?
Mm-hmm.
So why would one move away from the current elliptic curve onto a curve cycle? Does that fit somewhere into other designs, or is it an improvement of some type?
So an elliptic curve, or elliptic curves, are the backbone of modern cryptography. We generally refer to it as elliptic curve cryptography. Um, and elliptic curves, I'm not going to exactly say they're interchangeable, yet they're decently interchangeable. Bitcoin uses one called SECP256K1, which is a elliptic curve targeting roughly 128 bits of security. Monero uses ED25519, which is an elliptic curve targeting roughly 128 bits of security. I think technically it's like 122, but that's not enough of a difference to matter here. Both of them are perfectly valid choices for a 128-bit an elliptic curve with 120 bits of security. Bitcoin has used their curve for this long without issues. Monero has used ED25519 for this long, largely without issues. There was this one aspect back in the day, not worth getting into. So elliptic curves are, trying to think of the best way to explain it. They kind of have two different types of numbers. They have one type of very large big number, and this makes up your private keys. So when you're creating a private key, you just select a random, very, very big number. Mm-hmm. And then when you convert it to a public key, the public key is actually mathematically a point. If you remember in like high school doing graphs with like X and Y coordinates, yeah, a point is or a public key or a point has an X and Y coordinate. And these X and Y coordinates are also very, very big numbers. The distinction is that the big numbers for your private keys and the big numbers for the X and Y coordinates, they're actually two different big numbers. The private keys go up to 1 million, and the X and Y coordinates go up to 1,000,010, or whatever the random numbers are. Obviously, those are bogus. And that doesn't sound too different, but yes, those numbers being different has very, very large implications. So what a curve cycle does is a curve cycle is actually two elliptic curves. It has one elliptic curve, which uses 1 million for the private keys and 1,000,010 for the X and Y coordinates. And then it's another elliptic curve, which uses 1,000,010 for the private keys and 1,000,000 for the X and Y coordinates. So they kind of flip back and forth on each other. One's private keys, the other one's X and Y coordinates, and vice versa. And this is all a very, very drastic simplification of the actual cryptography being worked with. So definitely don't go to a college professor and be like, oh yeah, no, this dude called Kayaba told me this is how it was. No, this is just a very drastic simplification. So a lot of times with zero knowledge proofs, the proofs do define variables. And these variables, zero knowledge, you can't access them. The variables are frequently the private keys, these numbers, which is why when you do a signature, you're not revealing your private key, you're only revealing your public key. So then the efficiency issue, the kind of reason for a curve cycle with all these zero knowledge proofs is, okay, so we have a zero knowledge proof. The variables are these quote unquote private keys. Eventually, though, it generates public keys. It generates points. These are the proving data, and it moves forward. So the issue is, okay, it generated a public key, but we want to use the public key as a variable. We want to do more operations on it. But we can't cram the public key into a private key. There are two different types of numbers. So what we do is we take the public key and we move it to a different elliptic curve where it is a private key. And then it's once again a variable, and we can do all of these zero knowledge operations on it, so on and so on. But if we couldn't convert it back into a variable, it would be very, very slow to work with, and it would be very annoying and complicated, and it would be hundreds of times slower. Obviously, very drastic simplification. I hope some of that at least made sense.
So, in effect, what sort of increase in privacy does
curve
it give
cycles? Well, it's not about privacy. It's really about efficiency. Curve cycles just let us make very complicated zero-knowledge proofs because they allow you to... I don't know a good way to simplify it, but basically they just allow you to make very complicated zero-knowledge proofs that are also very efficient.
Okay, cool. Is there anything else you'd like to mention?
Just hopeful for Monero's future. I think there's a lot ahead of it. We'll see exactly what the timeline is on it. Uh, Obviously, Luke Parker, if you want to follow me on Twitter, it's at KayabaNerv. Also the lead developer of Sarai Dex, so maybe check that out. But yeah,
I'll link that all in the show notes below. Luke, thanks so much for coming on, man. You shared some great
yeah,
knowledge, and
thank you for having me.